Hello, my name is Liviu Drughean, and I'm trying to present in a few moments, in a few minutes, my presentation, which is, let's say, according to the season. It's winter, so I will present ice rink, and the name, as you can see on the first slide, it's using natural refrigerant on ice rink plants. It's not running, okay. I have designed in Romania a lot of ice rinks, around 20, let's say. And I already have a good team in which I work in Technical University for Civil Engineering in Bucharest, Romania. This paper is about a refurbish of old ice rink, which is placed in Miercurea Ciuc. It's a main city of Romania. And this old ice rink was made in years 70. And in that time, the designing plants were with direct vaporization plant. This ice rink have served many years, and the plant was using ammonia like a refrigerant, but in a variant with direct evaporation. So the total quantity of the refrigerant in this ice rink plant was around 5,000 kilos. That means a lot, and taking into account the new regulation for safety, it's almost impossible to use such a plant for an indoor ice rink. That's why I try to change a little bit designing of this ice rink, and I have choose to make indirect vaporization using also ammonia, and I have choose ammonia again, taking into account a lot of refrigerants. In these slides there are only 4 of them. And if you take into account all the data which are here, which we have calculated using the theoretical cycle, you can see that we can choose 2 refrigerants, ammonia and CO2. But I will come back in the last slides to show you also an analysis of risk of using CO2 for ice rink, which determine us to choose ammonia. In this case, for having the cooling power for this ice rink, for this indoor ice rink, which is the cooling power is around 400 kilowatts, sorry. The total load of using ammonia is only 50 kilos. That means a reduction from 5,000 kilos in the first plant to the second one, the newest plant, 50 kilos. That means a reduction of 1,000 times. 50 kilos, that means almost nothing. Sure that in this case we have used also secondary loop for the brine, for transferring the temperature to the ice rink slab. And in this case we have used a mixture between water and glycol with a concentration with 30%. But let's take some view to the general data. And the artificial ice rink, indoor ice rink from Merkurachuk, it's according to the laws of the Hockey Federation, International Federation, 60 by 30 meters. That means 1,800 square meter. And according to the quality of ice, because this ice rink is also for professional sports and also for leisure, we have to achieve for hockey hard ice, which is usually between -5 to -7 degrees Celsius. For artistic or figure skating, it's -3 to -4 degrees Celsius. That means a dry ice. Or for leisure would be -1 to -3. It's usually a soft ice or a humid ice. In this case, also the temperature which we must have in the brine loop, it's according also to the temperature of the ice, and also must be according to the temperature of the outside temperature, because such an ice rink is running 11 months per year. That means almost the whole year. That's why the temperature of the brine, not the evaporator, for the brine, it's -9 to -7 for +5 degrees Celsius, -10 for an outside temperature around 10 degrees Celsius, or if it's warmer outside, the temperature must be less than -10 degrees. That means that the temperature in the evaporator it's lower around 3 degrees Celsius. Also, we must take into account that the thickness of the ice must be from 3.5 to 5 centimeter, because we have to have a structure for the maintenance machine, which is coming from time to time to refurbish the surface of the ice. The refrigeration plant, as I told you, in the brine is a solution, a mixture between water and glycol with 35%, around 35%. And the temperature of the outlet circuit for the brine is around -12 degrees Celsius. Also, the necessary code for making the ice, it's a little bit bigger, and for cooling the ring slab, for starting making the ice, usually for such a surface of 1,800 square meter, we need for an indoor ice rink 450 till 500 kilowatts. And also for making the ice, we need a cooling load around 3 to 350 kilowatts. And for making the maintenance of the ice, we need 100 till 150 kilowatts. So it's not the same cooling power every time, and also we must take into account this fact for choosing the machine which is making the ice. So in this case we have choose an ammonia chiller. It's a Sabroe, you know better now, it's York, around 400 kilowatts, which is formed by two compressors, And this machine have been chosen for making the refrigerant, the cooling plant for this ice rink. Also, we have an advantage here using such a machine with ammonia, because it's very compact. And so the dimension of the refrigeration building, it's around 12 by 13 meters. And the distance in this case from the machine to the ice rink slab, it's around 14 meters. Here it's the cooling plant. I can use the microphone, the portable one. Okay. Does it work? No, no. Okay, I will try to use my voice. No, no, no. Oh, this one, because I want to use the laser. Why? It's another question. That's why I have choose ammonia, because you know that ammonia, the vapor of ammonia which are coming from the compressor are very high, like the temperature of this vapor it's very high. And so in this case we can it's better. It's all right. Okay, and in this case, after the compressor, here is the chiller with compressor, evaporator, condenser. Between compressor and condenser, we have put it here a heat exchanger for making a recovering loop for preparing hot water. Why hot water? Because in the case of ice rink arena, the sportsmen after the match are going to the bath, doing a shower. And so we can make some energetical recovery here, and we can prepare the hot water in the same time that the chiller is running. Another nice loop, in my opinion, it's here. You see, the condenser, it's cooling by a liquid. In this case, the liquid is going to a dry cooler which is standing outside. Because this city, Miercurea, it's a pole of cool in Romania, and usually there are a lot of days with temperature which decrease just till minus 15, minus 18. I have put it here like liquid, the same liquid that we use like brine to the ice rink slab. And in this case, you see here there are two valves. When the temperature is going down under minus 10, we can stop the chiller, and the brine from the ice rink slab is going dry cooler. And so we can make a lot of economy, and it's a wonderful loop for recovering energy. Almost after a couple of years that this ice rink is running, there are months, let's say there are days around 60, 70 days per year in which the compressor is not running. Yeah? And this also, it's very interesting because in this case, using this kind of machine with a condenser cooled by a liquid could make in a place like this good recovery loop. Here there are some photos from the works on this ice rink. Here are ducts, the pipe from the ice rink slab, which are going in the technical channel. Here it's the dry cooler, which is outside. And here it's the chiller, which I told you that it's equipped with 2 compressors. And it's Subroy, you see here the white ware, and the brand, the general brand, CO. Here it's not possible to see. Here, after the compressor, it's the evaporator, and here on top, it's the condenser. Let's discuss a little bit about what are the reasons for choosing the ammonia instead of CO2. Usually ammonia, you know, it's a flammable refrigerant. It's very dangerous if you don't know how to design and how to operate. But also the old tradition, because ammonia is one of the oldest refrigerant, it's almost well known how to design and how to use this refrigerant. Also the charge of 50 kilos, it's almost nothing, even in the case that would appear an accident and the whole amount of charge is going out. The CO2 system usually are nowadays it's used in supermarkets, or it's used for replacing the CFC or HCFC refrigerants. This refrigerant, okay, has good properties, thermodynamics properties, but don't forget that at 30,000 ppm in volume, he become a lethal agent. Yeah, and in the case of fracture or rupture of a tube from the slab, the quantity of the CO2 would enter into the arena, and in this case, the player's bench or the spectators which are in the lower rows would suffer a lot, would even stay there and to have some very grave accidents. Also, in the house of the refrigerating plant, if a hot gas line is fractured, also we can depass this lethal concentration, and this must arrive to have an accident with the guys which are doing the maintenance of the system. Yeah. Also, don't forget that after 31 degrees Celsius, CO2, it's leaving the subcritical point, and this condition would arrive easier in summer, and in this case we have some problem with opening valves which protect the equipment which is in the refrigerating house, and so also a quantity of CO2 is coming out and would depass this concentration, this lethal concentration. In conclusion, the artificial ice rink from Mirkanchuk, it's now conform to the local and international regulation. Also here, for the refrigerating plant, it's used natural and ecological refrigerant, it's ammonia, which have ODP 0, which have GVP 0, and also you have seen in the table that I have presented earlier, that the heavy factor is almost the smallest one. The quantity of the 50 kilos of charge which is inside the chiller would not reach the condition for explosion even if we have an accident into the house of the chillers. Also, I want to say something more, because I want to improve this plant, and now I'm making a new study for changing the brine. In this case, as I told you, it's a mixture between water and glycol. For the future, I want to use a mixture between water and ammonia. Ammonia is not only a good refrigerant, but could become a very good secondary fluid. Because in this case, using water and ammonia after the calculation that I have made on the paper only, it's a decrease of the energy for pumping. And in the next time, till to the next KGH, the next one which will be a jubilee, I want to have some results and to arrive with a new plant, a better one with some energetical recovery loops better than in this plant that I have presented today. Thank you very much, and I want to see you also next time.